Hello everyone, we're going to work one more semantic trees problem. This is a problem that sort of has everything, it brings it all together. You see the problem at the very top of the page. We are going to show that this argument is quantificationally invalid. And let's take a look at the argument and see what all it's got going on in it. We do have both the existential quantifier as well as the universal quantifier. And we have nested quantification, quantifiers inside the scope of other quantifiers. We have also all 5 of our truth functional connectives. We have the ampersand, the tilde, the wedge, the horseshoe, as well as the triple bar. We have an identity to work with, y equals x there at the tail end. We have names to work with, the name r and the name g. And finally, we have both one-place predicates, cx, as well as two-place predicates, h and l. So we get to practice lots of our skills. I'm going to ask you to practice along with me. I think this is best. So why don't you go ahead and pause this video. I'll ask you to pause it periodically. Go ahead and pause this video and get a piece of paper and a pencil, and then go ahead and copy down the 2 premises. I've already copied down those in my workspace. So go ahead and copy down the 2 premises, and then at that point you can unpause the video and we'll proceed. Okay, so what we're going to do then is start to think about how to get started, and to do that, as you know, we have quantifiers to work with. The first thing we need to do is decide what is going to start our interpretation. So we got to have a universe of discourse, and I'm going to go ahead and tell you this problem has to have a 2-element domain. It can't be solved with a 1-element domain. Our interpretation will eventually have to specify an extension for our 1-place predicate C, our 2-place predicate H, our 2-place predicate L, and our 2 names, I'll put them here, G and R. Normally we would be working out what the denotations of G and R will be, but I'm going to go ahead and cheat a little bit and simplify things. I could say this is trial and error, but I've already worked it out. One solution is attainable by assigning G and R to the same object, and we'll just let those pick out the number 1. So we're going to know ahead of time what we'll be doing with those G's and R's in our semantic trees. What I'd like to do now is pause the video. Knowing that we have a 2-object universe, I'd like you to draw the tree under this existential generalization. So pause now, work that out, and then when you unpause it, you can see how I worked it out. Okay, hopefully you didn't struggle too much with that. I'm going to go ahead and diagram this existential generalization. Again, it's an existential. The main logical operator is that quantifier. What that means is that its truth value is determined by the truth values of its instances, and that's what we're going to branch to. We will always branch to those expressions that determine the truth value of the sentence above it. So we're going to drop the quantifier and focus on the quantified formula Cx ampersand Hxg. We're going to copy that down twice, replacing the x with 1 on the left branch. C1 ampersand H1G. And then over here C2 ampersand H2G. When we look at these 2 instances of the generalization, we see that they are conjunctions. And what determines the truth value of a conjunction? The truth value of the conjuncts. So that's what we're going to branch to. C1, H1G. And over here, C2 and H2G. C1 and C2 are logically simple and they don't have any names in them, so the tree stops growing there. However, H1G has the name G, and we've decided that we're going to let G denote 1. So we're simply going to recopy those. We'll drop the G and replace it with 1. And that is the completed semantic tree for the existential generalization, our first premise. What I'd like you to do is hit pause again and draw the tree under this universal generalization. When you unpause it, I'll work it out. Okay, so the universal generalization also has two instances. And these are long instances. So we will be dropping the quantifier. We'll also drop the opening parenthesis. We're going to drop the parenthesis at the tail end as well. Everything else, though, between that tilde and that R, we're going to copy down at the ends of these two branches, with one exception. We'll be replacing these three G's here, here, and here with a 1 on the left branch and a 2 on the other branch, and we're not going to make any other changes. This is a point where you can actually end up making things more complicated than they need to be. So just copy everything without making any changes except the replacement of the variable x with the number 1 here. So we'll start with that. Leading tilde, open paren, tilde, H, 1, G, wedge, tilde, C, 1, close paren, horseshoe, L, 1, R. And do the same thing over here. Leading tilde, open paren, tilde, H, 2G, wedge, tilde, C2, horseshoe, L, 2, R. These two instances are conditionals. The horseshoe is the main connective. Look at that tilde out on the left, as followed by an open paren that closes here in the middle. That means that tilde does not have full scope. The connective, the main connective, is this horseshoe. So we simply copy down the antecedent, tilde open, tilde H, 1, G, wedge, tilde C1, and then L, 1, R. And we're going to do the same thing on this conditional, just break it apart. If we look at the antecedent of the conditional, the main connective is that tilde, so we drop it. And we're going to drop the outer parens that go with it. So we have tilde H, 1, G, wedge, tilde C1. We do the same thing here. Tilde H, 2G, wedge, tilde C2. And then we work on these wedges. Tilde H1G is the left disjunct. Tilde C1 is the right disjunct. Tilde H2G, tilde C2. We drop those negation signs, H1G, C1, H2G, C2. Finally, we have logically simple expressions across the bottoms of all these branches, but some of them have names. This one has a G, so we'll replace the G with 1. H11. This one has a G, H21. This one has an R, L11. This one has an R, L21. Okay. Now the semantic tree for the second premise is complete, and it's time to work on our conclusion. So I'll start that here. I think I've got room. You know what? I'm going to move it over here. And then I'll just branch out. So there's an X for all Y, LYR, triple bar, Y equals X. What I'd like you to do now is pause the video and draw the entire semantic tree under that conclusion. Okay, let's see what this looks like. I'm gonna spread out. I've got quantifiers inside the scope of other quantifiers, and that's gonna get a little bit bushy. So this is an existential generalization. We drop the existential quantifier, and then we recopy everything to the right. We're going to copy it down twice, one at the end of each branch, with one difference. This X that we see here, which is the variable of quantification for our existential quantifier, we're going to replace that X with a 1 on the left branch and with a 2 on the right branch. So for all Y, L, Y, R, triple bar, Y equals 1. And then over here, for all Y, L, Y, R, triple bar, Y equals 2. The universal generalizations now also have 2 instances. We're going to drop that universal quantifier. We're going to drop the 2 parentheses. And we're going to focus on this expression, LYR triple bar Y equals 1. We're going to replace those Y's with 1 on the left branch. L1R triple bar 1 equals 1. L2R triple bar 2 equals 1. L1R triple bar 1 equals 2. And L2R triple bar 2 equals 2. We'll break these biconditionals into their components. L1R 1 equals 1. L2R 2 equals 1. L1R 1 equals 2. L2R 2 equals 2. The last thing we need to do is replace R with its denotation. That's a 1. Okay, So there we have our three semantic trees. They have all been drawn out completely, and it's time to sort of revisit what we're doing here. This is an argument that is quantificationally invalid, and we are to prove that it's invalid. And what that means is we need to look for an interpretation that constitutes a counterexample. It's an interpretation where the premises are both true and where the conclusion is false, right? So let's think a little bit about this. In order for an existential generalization to be true, at least one of these two instances has to be true. It could be the one on the left, could be on the one on the right, or it could be both of them. So we're not going to force anything down these paths just yet. For a universal generalization to come out true, however, both instances have to be true. But those instances are conditionals, and there are many ways to make a conditional true. Could have false antecedent with a false consequent, false antecedent with a true consequent, or both components being true. The conclusion is an existential generalization, and we want it to come out false, and that means all of its instances have to come out false, all of them. Its instances are universal generalizations, however, and there would be many ways in which the universals could come out false. So I want to stop there and let you try to have a go at it. So if you would hit pause on the video and see if you can start working out some T's and F's that will hang neatly together and help you find the interpretation or an interpretation that constitutes a counterexample to this argument. Go ahead and hit pause and we'll resume in a moment. Okay, so there are a few things we can do. You know, this is a lot of trial and error. I like to start with the first premise if I can. And we said earlier that, an existential just needs it needs to have at least one true instance. There's nothing telling us that would be the left or the right. We can just make a choice. We can say, let's make this one true. If this comes out true, then the existential will be true, right? So what happens here? Well, the instance is a conjunction. So if the conjunction is true, both conjuncts have to be true. That's our truth functional logic helping us out there. Both conjuncts have to be true. And of course, when we say that H1G is true, that's the same as saying H11 is true, since 1 is the denotation of G. It turns out that this is a terrifically helpful move. A lot of action ensues from here. So once we see this C1 is true and this H11 is true, we got to come over here. You see H11 is true and that C1 is true. And it turns out that these bubble up nicely. So if H11 is true, H1G is true. If H1G is true, then the negation is false. Likewise, if C1 is true, then the negation is false. And this disjunction then has all false disjuncts. That's not a very clear F. I can do better than that. This disjunction has all false disjuncts, and that means that it is a false disjunction. But the negation of the disjunction then would be true. Okay? If we have a conditional whose antecedent is true, that actually tells us something about its consequent. If the conditional is true and its antecedent is true, then the consequent has to be true. It's actually the basis of conditional elimination or modus ponens. And if L1R is true, then L11 is true since 1 is the denotation of R. Okay? So this choice over here actually helps us to make sure that this instance of our second premise comes out true. If I look at this L11 down here and I see that it's true, I got to come down to my conclusion and recopy that in a couple of places. We're going to see what happens. If L11 is true, L1R is going to be true. We do know that 1 equals 1. That's just a true statement, true on all interpretations. And we know that a biconditional that has all true instances, a biconditional with both true components is a true biconditional. But something's happening here. If we have a universal generalization that needs to come out false, it has two instances, one of which is true, that tells us something about this other instance. It has to come out false. Okay? So if we look below the biconditional, we see that 2 equals 1 is one of the claims, and we know that that statement is false. 2 does not equal 1. If we have a biconditional that's false, and one of its components is false, that tells us the other component has to come out true. Biconditionals are false when their left-hand side and right-hand side have different truth values. So if L21 is true, if L2R is true, L21 is going to be true as well. So we're going to come over to this L21 and copy down that T. And then some interesting things happen. On the right-hand side of this semantic tree for the conclusion, 2 equals 2 is a true statement. L21 is true, then L2R is true. A biconditional with both true components is a true biconditional. But we want this universal to come out false. We really need for this biconditional to come out false, and it will. So if L11 is true, L1R is true. We know that 1 equals 2 is simply a false statement on all interpretations. A biconditional whose components have different truth values is a false biconditional. So that works out really nicely. I am going to take this L21, the T under L21, we got to copy it down up here. Up here. We always have to maintain consistency with our truth value assignments at the bottoms of these trees. If L21 is true, then L2R is true, and that alone secures the truth of the conditional. Conditionals with true consequence are true conditionals. So we're kind of home free at this point because we don't have any T's and F's assigned here yet, and we do need them, but it won't matter what we do because this conditional is going to be true just by virtue of the truth of its consequent. Over here, it also doesn't matter what we do because the truth of the existential generalization is vouchsafed by the truth of its instance on the left. We could also notice similarities between those two open parts of the trees, C2 and H21. C2 and H21 are the basic components here. So we can just make a decision. And I've said before, my habit is to make things false when I can get away with it. It makes for very simple interpretations at the end. And we can see what happens here. We just make sure nothing goes astray. If H21 is false, then H2G is false. And a conjunction with false conjuncts is a false conjunction. And that's fine. The existential generalization only needs one true instance, and we've got it. Okay? So we're going to copy down those F's at the ends of the tree over here under the second premise. And we're going to see what happens. H21 is false, then H2G is false. That means the negation of H2G is true. If C2 is false, then the negation of C2 is true. And we know that a disjunction with two true disjuncts is a true disjunction. And the negation of that would then be false. And that's okay. The conditional will be true if its antecedent is false. So this is what our completed trees look like with all the truth values plugged in. And they're all consistent. So now it's time to construct our interpretation off of our trees. What we're going to see over here is that C1 is true, C2 is false, okay? C1 is true, C2 is false, and that means that 1 is in the extension of C, but 2 is not. We have to leave 2 out. When it comes to H, we can see that H11 is true, but H21 is false. Okay, so we don't see in any of this, because of how we assign the denotation of the name G, we don't see H12 anywhere, and we don't see H22 anywhere in our trees. So they don't really come up, and we can leave them out. Well, what this means though, H11 is true, H21 is false. What this means is that the pair 1, 1 is in the extension of G, but nothing else is. Okay. So let's take a look at L. We can see that L11 is true, and L21 is also true. Again, we do not see L12, and we don't see L22 anywhere. But since both of those had to be true, we've got the pair 1, 1 in the extension of L, and we've got the pair 2, 1 also in the extension of L. Okay? So that is our fully worked out interpretation. It constitutes a counterexample to this argument because the premises are true on this interpretation and the conclusion is false. And our semantic trees demonstrate that this interpretation is a counterexample to this argument.